Helena and Milton, and Jim for giving me the opportunity to speak today. I will talk about the Harnack inequality for elliptic and parabolic equations with low regularity of the drift. This is a joint work with Igor Kukavica and Lenya Rizhak. We are interested in the qualitative properties of solutions to linear scalar drift diffusion equations. Here, the drift B of xt is a given vector field. More precisely, we are interested in the following two questions. Can the standard regularity assumptions on the drift term needed for the Harnack inequality to hold be relaxed if the drift is divergence-free? And can we get any regularity results if the drift is supercritical and divergence-free? First, to tell you why we are motivated, our main motivation to look at linear scalar equations with very low regularity on the drift is to study nonlinear equations where the drift can depend on the solution and the derivatives of the solution, for which we don't have any smoothness. Some examples for nonlinear equations with divergence-free drifts are the various active scalar equations, like the vorticity equation in 2D and the magneto-geostrophic equation. And in the case of fractional diffusion, for example, the surface quasi-geostrophic equation. Let me first recall the classical de Giorgi-Nash-Moser theorem in the case of elliptic equations written in divergence form. The theorem states that weak solutions to the equation are Euler continuous. And since in our approach we use Moser iteration, I would like also to recall Moser's Harnack inequality. For positive solutions to the equation, we have that the maximum in a compact set K of U is controlled by the minimum of U in K, where the constant depends only on the geometry of the domain, the compact, and the ellipticity constant lambda. In order to describe the regularity assumptions on the drift, let me recall the basic scaling properties of the solution. The solution basically remains invariant under the following two transforms. If UR is the rescaled function U, then it satisfies the drift diffusion equation with the drift BR. And we call the assumption on the drift critical if the norm of BR coincides with the norm of B for any R positive. Subcritical if the norm of BR is smaller than the norm of B on small scales, and supercritical if the norm of BR is larger than the norm of B in small scales. So in the subcritical case, we have that the diffusion term dominates the drift term, and strong regularity results are available by using linear perturbation theory. In the critical case, we have that the drift term and the dissipation term are balanced in all scales, so one usually expects to get Euler continuity. However, in the supercritical case, we have that the transport term dominates the diffusion, and regularity results present a challenge even in the case when the drift is divergence-free. So first, in the critical case, with no divergence-free assumption on the drift, we have so in the case of the elliptic diffusion equation, we have that the critical space is Ln, and the Euler continuity is known since the work of Stampacchia, and it was recently revised by Safonov. Notice that the Euler estimate, in the Euler estimate, the constants C and alpha depend only on the Ln norm of the drift. In the parabolic case, without additional assumptions on the drift lying in the critical space L infinity Ln, the Euler continuity is still open. However, it is known in the case when the drift is divergence-free. Now, in the case of critical divergence-free drift, Nazarov and Oratsova in 2001 significantly reduced the regularity assumptions on the drift for the Euler estimates, Harnack inequality, and Liouville's theorem by proving them for drift lying in the critical Morris space. Friedlander and Vico established the Euler regularity if the drift is in L infinity BMO negative 1. And independently, Seregin, Silvestre, Schwerek, and Zlatush established the Euler regularity, Liouville's theorem, and Harnack inequality with the same assumption on the drift. So notice that all these spaces have the same scaling. So we have that the Morris space is between Ln and BMO negative 1. So in the case of supercritical divergence-free drift, we obtain the following result. Suppose that U is non-negative Lipschitz solution, and B is divergence-free in the critical Lebesgue space LQ. Then we have that the supremum of the solution in a bow is controlled by the infimum with the explicit constant given in blue, which depends on the LQ norm of the drift and the radius. Due to the subcriticality of the assumption on the drift B, we have that this constant depends on the radius, and actually it blows up when R goes to 0, but it's bounded for R going to infinity. In order to, so a sufficient condition for the drift term to remain bounded is to use that U is a Lipschitz generalized solution. Our results also hold for weak solutions, but one needs additional assumptions on the drift. It is an application to our Harnack's estimate, the one-sided Liouville's theorem. One-sided means that the solution is bounded only from one side. Here, we take the solution to be non-negative, bounded from below. So basically, if B is divergence-free in the critical space LQ, then the equation considered on the whole space, and if we consider the solution of the equation of the whole space, then the solution needs to be a constant. So regarding the proof, the proof is basically based on Moser's iteration. We compare the supremum on the solution on a small bow, the infimum of the solution on a small bow, to the two LP norms in a larger bow. Basically, the solution goes in the following two steps. First, we prove that subsolutions are locally bounded, and in the second part, we prove that we establish a lower bound on the infimum of supersolutions. So for the second step, one have that if U is supersolution, then 1 over U is subsolution. And using the local boundedness, obtain that the supremum of V is less or equal than a constant, the LP norm of V on a larger bow, which implies the following lower bound on the infimum. And it suffices just to bound the integral, the product of the integrals in blue to obtain the lower bound of the infimum. For this reason, one can just note that it's enough to obtain a bound of the following exponential integral of exponential of some p naught absolute value of W, where W is the log of the solution minus the average. So in order to establish this exponential bound, we do that in several steps. First, we need to establish L2 bound on the gradient. And then for the higher norms, we have an inequality which looks like that, which we iterate at the end of the day. In the more challenging parabolic case, we have the following theorem. So once again, we suppose that the solution is non-negative Lipschitz generalized solution in the space-time domain. It is, we suppose that the drift is divergence-free, and it's in the space LP, LQ, and in L infinity, L2, with the exponents satisfying this inequality. So this is basically supercritical condition. Then we have that the supremum of the solution on a cylinder translated backwards in time is bounded by the infimum of the solution with the explicit Harnack constant. So notice that here we have one additional assumption on the drift, which we managed to reduce in the elliptic case by performing one additional iteration. However, here we couldn't get rid of this additional assumption. And it's basically needed in the first step of the Moser iteration. Regarding the continuity, let me just mention two results in 2 dimensions. So the first result is a result for discontinuity. Suppose that the drift is divergence-free and it is in the critical space L infinity LP for any p less than 2, then the solution becomes discontinuous in positive time. So here the drift depends both in space and time. However, if the drift depends only on space, so it's time independent, and it's once again in a supercritical space L1, then the solution remains continuous. So as an application of our Harnack inequalities, we obtain the following continuity result. So here we consider a solution to the so this is the elliptic version of the theorem. We also have it for the parabolic equation. So say that U is a solution of the elliptic equation in any space dimension. And if the drift is divergence-free and lies in the locally logarithmic Morris space, which is slightly supercritical, then the solution is continuous. So notice that the Morris space is a generalization. The logarithmic Morris space is a generalization of the classical Morris space when alpha is strictly positive. And thank you very much for your attention.
Any very quick question?